So, what we're going to talk about is the orthogonal symmetry. First, let's start with a reminder of what is a linear symmetry, okay? Uh, so, sorry, that wasn't the one intended. All right, so what do we need in order to do a nice linear symmetry? We need, well, we are in a space E, and we need F to be, E to be the direct sum of two spaces F and G. And you remember, we're going to do the symmetry with respect to some space. In our case, we usually need that one F, and along a direction G. So, for instance, if you're in R2, that could be, so you need two non-collinear directions in order to make a direct sum for R2. And any x, you know that any x that in R2 can be described as one piece that belongs to x1 that would be to F like this, and one piece that belongs to G like this. And so x is uniquely written as x1 plus x2, so the unicity comes from the fact that it's a direct sum. And when we're doing the linear symmetry, you know that S of x is, we keep at the x1 part and we take the opposite of the x2 part. So that's going to send us on the other side of that direction F, and we take minus x2, and that's going to be S of x. Okay, and one way to characterize the symmetry, so just we see that S of x is the x1 part minus the x2 part. And so we know that one way to characterize symmetry is that, well, if you apply the symmetry again, well, you're back where you started. So one way to characterize the symmetry is to say that S squared is the identity. Okay, that's what we get here, all right? And when you have, so if you want to check out that you've got, you really have a symmetry, you have to check that if you apply twice your linear map, you're back where you started and it corresponds to a symmetry. Now, if you want to find the corresponding characteristic spaces of that symmetry, they are going to be given by this relation. F is the kernel of S minus identity. What does it say? It says basically that anything that belongs to F is going to, well, stay where it is, okay? So S minus the identity, S minus I, d of x is equal to 0. If you read the description above, it means that the x2 part is equal to 0. Okay, so that anything that belongs to the kernel of this map, S minus identity, is actually on F, or S is equal to the identity. Okay, that's another way to state it. The other part, when we say, so that gives you the direction F, the symmetry axis, or symmetry plane, or symmetry space S. And if you want to find the direction of that symmetry, the G space, well, it's going to be the one S plus identity of X is equal to 0. So if you see in that stuff here, in that relation, you make S plus identity of X, that's going to be equal to 0 if the X1 part is equal to 0. Okay, and so that is when X belongs to G. And it gives you, if S plus identity of X is equal to 0, it gives you that S of X is minus, is the opposite, negative X. So it's going to be sent, anything that belongs solely to G is going to be sent to its opposite vector, to its opposite element, directly on G itself. Okay? So you remember we had some exercises where you were given a matrix, a square matrix, how to check that you had a linear symmetry. You had to check that if you square the matrix, you get the identity. And to find the characteristic spaces F and G, well, if you are in R3, I just want to remind you that if you are in R3, we can have, so that could be your space F, that would be a plane, and you could have whatever direction G that doesn't belong to that plane. And again, you have the same ID that you have the projection on the direction of G, and that gives you the x1, the x2, and so you can make the symmetry with respect to F on the direction of G, and that gives you the same stuff here. That would be S of x. Okay, the symmetry with respect to x, but we could also do the contrary. You could take the symmetry with respect to G on the along the direction F, and that's the same idea. Okay, you keep the one part and take the opposite of the other one. All right, so when you have a matrix, you just check that if you square the matrix, you get the identity matrix, and that's one part. And next part, you have to check that if you want to find the F and G directions, you have to find the kernel of S plus identity, that's going to be the G, and S minus the identity, that's going to be the F. So now we're going to go to orthogonal symmetry, and actually it's something that works even better. It's just what you wanted to do with those kind of symmetries before. Um, so yes, indeed, orthogonality brings us a lot of things that work really more intuitively in a nicer, in a more direct way than non-orthogonal stuffs. So what we're using is that our space E is, we saw that earlier, could be described when you have a subspace F as the direct sum of F and its orthogonal. So now what changes compared to our previous case is that we have two orthogonal spaces, F and G, or if you're in R3, you really have two orthogonal spaces, F and G. Okay, that would be one example. All right, so you've got a nice orthogonality between those two spaces, and well, actually, G is equal to F orthogonal. All right, so that now, and then it works exactly the same, except that it works even better in a sense. So any x is uniquely defined as the sum of x1 and x2. The nice thing is that now this sum can be expressed with an orthonormal basis. And that orthonormal basis comes very simply by just concatenating an orthonormal basis of f and an orthonormal basis of f orthogonal of g. Okay, so but again, it's going to be the same idea. You've got some x1 part, some x2 part. So here that would be the x1 part, the x2 part, and again we get that x is equal to x1 plus x2, and you're going to say that s of x is going to be so x1 minus x2, so exactly the same thing. You keep the x1 part and you take the opposite of the x2 part, so that brings you here. Okay, and if you're doing the same symmetry with respect to f, it brings you here. Okay, and it's just that the direction, you don't have the choice of many directions, it's just going to be the orthogonal direction. Okay, so let's sum up what we have. Okay, let's see what's written here. All right, the orthogonal symmetry with respect to f is the symmetry along f orthogonal. If f is an hyperplane, so hyperplane dimension n minus 1, then we say, it's just a definition, that it's called a reflection. All right, so what are the important points here? So we have that, again, the basic characterization of symmetry is that if you square it, if you apply it twice, you're back where you started. Okay, so that's something that is always true. If S composed with F is equal to the identity, not especially for the orthogonal one, but in general, it just means that S minus 1 is equal to itself. Okay, it's auto-inverse, right? S times S, or S compressed with F, you know it's the same thing. It's equal to the identities. It just means the inverse is S itself, okay? Next, but that is always true. So again, the symmetry is going to be defined as we keep the x1 part and we subtract the x2 part, and F is the same thing as S minus the identity. The direction is going to be S plus identity, which is exactly the same stuff. But what's nice result here is that in an adapted basis, the matrix of S is diagonal with plus ones and negative ones on the diagonal. So we're going to see that a bit just afterwards. The spectrum, we've already worked on that. That was one of the exercises. It's going to be included in -1 and 1, and the order of the for instance, the one eigenvalue is going to be equal to the dimension of F, and the order of the -1 eigenvalue is going to be the dimension of F orthogonal. So just because of the previous property, right? Well, this is how we can write our matrix, the matrix of the symmetry. Okay, so then we have that an orthogonal symmetry is a linear isometry. Okay, and a symmetry is orthogonal if and only if its matrix is in an orthonormal basis is symmetric. So let's see about that. First part, an orthogonal symmetry is a linear isometry. Okay, remember, so we have, assuming we have a matrix representation of F, for instance, you get that M squared is equal to the identity. Okay, so what does it give us? It gives us that M minus 1 is equal to M itself. And we are going to use one of the previous results that tells you that an endomorphism is orthogonal if and only if its matrix in an orthonormal basis is orthogonal. So let's see what we get here. Sorry about that, I have to. So let's see what we said earlier, that what is going to be the representation in an orthonormal basis. The good thing is that if we have F that has an orthonormal basis E1 up to EP and F orthogonal that has a basis, well, you know that we can complete the first one, the basis of F. We can find a basis of F orthogonal, which of course is going to be orthogonal to the previous one, and it's going to complete the one into a basis of E. That's why it makes a direct sum. So we can directly write it's going to be EP plus 1 up to En. All right, and so that if you concatenate the two bases, so they are all orthonormal bases. Okay, so that if you concatenate the two bases, you get an orthonormal basis of E itself, of the space E itself, as E is F plus F orthogonal as a direct sum. So if you're trying to make the matrix of this orthogonal symmetry, what do we get? So you know that you should take as the columns the images of the basis vectors S of En in E1 up to, so we get EP, we get En, EP plus 1. So what do we get? So answer in the next video.